Alright, so solving quadratics with roots. Like I said, any quadratic that can be solved by factoring has rational solutions. The answers will either be fractions or whole numbers. But not all quadratics can be factored. If we look at this example, it's already said equal to 0 for us. Is it a binomial or trinomial? So you ignore the 0 and say binomial. Can they both be square rooted to make whole numbers? No. Square root of 18 is not a whole number. Do they have anything in common that can be divided out?
No.
No. So this is not a greatest common factor problem. So this problem could not be factored. Okay, but it still has a solution. So if they cannot be factored, solutions still exist. If they cannot be factored, solutions still exist. But they are either one of two things. Well, first, if all of the answers that can be done when you can factor are rational, then if it can be factored, the answers are going to be irrational. And if you remember the number sets from chapter 1, section 1, there was irrational, there was rational. Those are both types of what kind of numbers? Real numbers. If it's not a real number, it's a imaginary number. So they are either irrational or imaginary. Imaginary is not covered in this section. This is actually is not even a section in your textbook. What we're covering today, guys, is supposed to be, you should already know how to do this. In all the years that I've taught Algebra 2, no one has ever known how to do this coming into Algebra 2. So we're covering it. It's just for the sake of it never gets taught in Algebra 1 because it's towards the end of the book. And you never get through the entire book in a math class. Yeah, our textbook has 13 chapters. We will only get through 8 of them. If we were to cover all 13 chapters, instead of doing a section every 2 days, instead of doing a section and then a day of practice and a quiz and then moving on, it'd be a section every day. It'd be new material every day. We'd be doing notes every day of the year. And then you would just be doing practice as homework. There would be no class time for practice. So we're only covering 8 sections. So this is usually does not get covered in Algebra 1. So we're going to go over it right now. Just something to recall. Irrational numbers are square roots of any number that is not a perfect square. So an example of an irrational number is the square root of 18. Or the square root of 7. Any number that cannot be square rooted to become a whole number. The square root of 16 is what? 4. So the square root of 16 is called irrational because it becomes the whole number 4. The square root of 18 is a decimal that goes on forever. If you type in, someone type in the calculator. It's 4 point what? 4.7. And then it goes, keeps on going, right? Alright, it goes on forever. It never repeats. It's an irrational number. One thing we didn't go over at the beginning of the year, I mentioned it briefly, is imaginary numbers. Those are square roots of negatives. The square root is the inverse of a square. What's the number 2 squared? 2 squared is 4. What's negative 2 squared? 4. So the square root of 4 is 2 or negative 2. The square root of negative 4. What number times itself makes negative 4? A negative 2 and a positive 2 make negative 4, but the definition of a square root is the answer has to be a number times itself, right? Yeah. So what that means is, here's how we write this answer, which we'll get to in the next couple of sections. What's the square root of 4? 2. But since this is a square root of a negative 4, the answer is going to be an imaginary answer. So you write the answer as this, 2i. The I represents the fact that it's an imaginary number because you can't square root a negative. Okay. It's an italicized I to represent that it's an imaginary number. Okay, we will get to that in the next couple sections. So, we need to be able to solve quadratics
Wait, how quick do you put these things on YouTube?
it'll be on there by the end of next period. It should be.
Well, that's good for the other classes, ain't it? They can go ahead and get the notes so they don't have to write them in class.
I guess, but watching the video, I wouldn't think this is beneficial as paying attention in class.
No, but they get more time to pay attention in class. Though.
I guess that's true.
Yeah.
We need to be able to solve quadratics that cannot be factored. Okay? So, the method one that we're going to go over, we're just going to cover just this method, is solving by roots. And before we get started, I just want to go over some vocabulary. If you read this, how would you read this? Square root of x. Okay? We're also going to read this, and you're going to hear me use this. It's actually, we're going to read it as radical x. Because the bracket that surrounds the x is called a radical. And what's inside of it is called a radicand. Okay, we're not going to go, that's not important. But it's just like a division symbol and then inside the dividend. It's a radical and a radicand. But the reason this is called a radical is because you're not limited to only taking the square root. You can also do a cubed root, which is what number 3 times becomes the number inside. So, for an example, the cubed root of 8 is 2, because 2 times 2 times 2 is what? 8. So, we're not only limited to square roots, so rather than calling it a square root, we'll refer to it as a radical. And then, what's 0 squared? 0 times 0. 0. What's 1 squared? 1. 2 squared? 4. 3 squared. Continue this list until you've gotten to the 12th square.
Are you giving us a worksheet today?
I am. This is the only section this is the only day that we're spending on this. Tomorrow we're moving into a new section. The new section uses what we're doing today, but this is not actually a section of its own in the book.
So, like, what will, like, later on life, what will we have to use this for?
You're not going to have to use it for anything unless you go into something specific to this.
Well, like, what jobs have to do with this?
In terms of I've highlighted. The numbers that I have highlighted are called perfect squares. The numbers that I have highlighted are called perfect squares. The perfect square list goes on forever. 13 squared is 169. 14 squared is 196. It goes on forever. We're going to stop at 12 squared. 144. The numbers that are highlighted are called perfect squares, and that's because they're the only numbers that when you square root them, the result of that square root is a whole number. So working these backward, what's the square root of 0? 0. What's the square root of 1? 1. The square root of 4?
2.
Continue writing that entire list up until you've got the 144th perfect square.
3, 4, 5, 6, 7.
You need to have these committed to memory or know how to create this list. It does not matter to me if you have these memorized or if you know how to create the list. But you need to know the fact that or 0, 1, 4, 9, 16, 25, 36, all the way up to 144 are the perfect squares. And you need to know that when you square root them, what's the result of that square root? Yeah, there's a lot of discussion in terms of moving into teaching more of a computer programming in computer programming at the same time as teaching concepts like this, because you're not going to manually do a quadratic equation. You're going to have some kind of, you can go on the internet and type in quadratic solver, and there's some website where you just type in A, B, and C, and it gives you the entire answer. Okay, someone's already programmed you can just go to Google and type it in, and someone's already programmed their website to where it has algorithms where you put in the coefficients of the quadratic, and it gives you the solutions of the quadratic.
You can pretty much find anything on Google, can't you?
So, we're going to take this list. This list you need to have memorized, and then we're going to move into using this, into the concept of simplifying radicals. Simplifying radicals. The process of removing perfect squares from a radical. The process of removing perfect squares from a radical. We're going to use this fact. This fact says the square root of a times b. If you've got the square root of two things multiplied, that's the same as the square root of the first times the square root of the second. Square root of two things multiplied is equal to the square root of the first times the square root of the second. So here's an example. Square root of 18. Is that rational or irrational? It's irrational. It's a decimal that goes on forever. We've already typed this one in our calculator. The square root of 18 is 4.2426, and then it goes on forever. So it's an irrational number. The ACT does this a lot. If the answer is going to be irrational, it gives it to you. It gives the answer in the most simplified form. 18 is not perfect, but if we go to our list, 0, 1, 4, 9, 16, 25, all of those, does any of those go into 18?
Yeah.
9 goes into it. How many does 9 go into it?
2.
Twice. So we're going to say, let's change the square root of 18 to the square root of 9 times 2. We're going to change 18 to 9 times 2. Now, when we do that, we're going to apply this fact. This fact says the square root of two things multiplied is equal to the square root of each of those things multiplied. Can either one of these be square root?
Yeah. 3.
Square root of 9. It's 9 times square root. What is that? 3. So we bring it to the outside of the radical. The square root of 9 is 3, so it can be taken out of the radical, and now it's 3 radical 2. Type in 3 square root of 2 in your calculator. 4.2426. The same numerical value. So we've not changed the number, we've just wrote it in what's called simplified form. That's another example. Square root of 16. That simplifies it to 4. That's one of our perfect squares. It's 4. Square root of 30. Now, here's the thing. The perfect squares are all the numbers that go, are all the numbers that we would need to technically, anything above 25, is that going to go into 30? No. Technically, we can take 30 and cut it in half. And that's 15, right? Nothing more than 15 is going to go into 30 evenly, right? So the only thing we need to check is our perfect squares that are smaller than 15. Taking out a 1 is redundant, right? Yeah. So does 4 go into 30?
Yes.
No, 4 is not going to 30. Does 9 go into 30? No. The next one's 16. 16 definitely not going to 30 because it's more than half. So there's no perfect square that goes into 30. So that's already been simplified. There is no way to simplify that.
Is that the only one? No. 61.
There's several that can't be simplified.
61 can.
Square root of 20. We would only need to check the perfect squares that go up to what? 10. Half of 20, right? So the only two that need to be checked are 4 and 9. 4 goes into it 5 times. The square root of 4 times 5. And which one of those can be square rooted? And when you square root it, what's it become? So the answer is 2 radical 5.
Okay. You can pretty much just do this without having to do all that 4 times 5.
Let's do the square root of 108. Half of 108 is what?
54.
54. So you need to check all the perfect squares that go up to 54. You need to check all the perfect squares that go up to 54. So Matthew, go ahead. 36. 36 is the largest one. 36 goes into 108 how many times? 3 times? So what's the answer? 6 radical 3. Okay. Now, when you look at this problem, you might not initially think 36 and 3. Someone said 9 and 12. If you said 9 and 12, that'll work also. Which of these can be square rooted? 9. So it gets pulled out and becomes a 3. So it's 3 radical 12. But 12 can be taken further. What goes into... What's the largest perfect square goes into 12? 4 goes into it 3 times. And when you square root the 4, what's it become? 2. So out here, you're going to have just a 3. You're going to have a 3 and a 2, which makes a 6. So you'll get the same answer. It just requires extra steps. Yes, sir.
So where did the 6 come from on the 36?
What's the square root of 36? That's where it comes from. You always square root the one that can be square rooted. And you pull it to the outside of this radical.
Is there any examples where the one can be square rooted?
Well, like the square root of 16 could have been written as 4 times 4. And what's the square root of 4? What's the other square root of the other 4? And 2 times 2 makes 9. So if they can both be square rooted, then that means it's the number above is also a perfect square. Good question. All right. Square root of 72. Square root of 147. And the square root of 7. Do those 3 on your own. Take 2 minutes.
Shouldn't take that long.
Here are the answers.
Sir, pull that down.
Okay. So, going back to that method, solving with roots. In order to solve with roots, we have to understand how to simplify radicals. And we're going to do 3 examples where we solve with roots. X squared minus 18 is equal to 0. This is the original problem we started with. It can't be factored, so that means we're going to have to solve it with some other method. Can this be done traditionally? Yes, because it's only got the x written once. So that means we can solve it just using order of operations backward. What's the first step?
Add 18.
Add 18. So we get x squared is equal to 18. What's the square mean? How many answers should we have?
2.
2. So when we square root, we've got to have positive and negative. So when we square root, we have to put x equals square root of 18, or x is equal to negative square root of 18. It's either the positive or the negative. You should have 2 answers. Now, if you simplify one, you can technically simplify both. 18 is a radical. It can be simplified. The largest perfect square that goes into it is what? 9. So it becomes, your answers are 3 radical 2 and negative 3 radical 2. Once you simplify 18, you know the answer for negative radical 18. So it's 3 radical 2, negative 3 radical 2. That's your answers. Now, if we wanted to check our work, we can just take this answer and plug it back in up here at the top. 3 radical 2 squared. If we've got multiple things inside parentheses, we just square it all. What's 3 squared? 9. What's the square root of 2 squared? What's the square root and the square root?
2.
They cancel, so it's just 2. And what's 9 times 2? 18 minus 18 is 0. That checks. Okay, so when you put it in the calculator, you go type in the calculator, you type in 3 square root, it opens up parentheses, right?
Yeah.
2, and then you hit square. You've got to make sure you put it in parentheses like this.
I did that.
Did you have 2 closed parentheses? Or just 1?
Oh. Yeah, you're right.
You didn't close the radical.
Yeah.
So you got to close the radical and then close the original parentheses. And then that'll give you 18. Okay. All right, second one. 4x squared minus 6 is equal to 74. We're not going to run through how to check if it can be factored. Technically, to check if it could be factored, you move the 74 over and you'd ask yourself, is it the difference of squares? We're just going to go straight to, it's a traditional problem because it's just got x written once.
Add 6.
So we just add 6.
Makes that 80. Undo that. Divide that 80 by 4.
Dividing by 4 makes x squared equals 20. You're going to square root, which means you should have how many answers?
2.
2. Radical 20. And negative radical 20. And then you simplify both. The answers are 2 radical 5 and negative 2 radical 5.
That's easy.
The largest number that goes into 20, that's the perfect square, is the number 4. And when you square root to 4, it becomes 2.
I'm used to it. I'm married.
All right, last problem. 2. 6x plus 2 squared. Anthony?
Sorry.
This is just solving a quadratic that's in vertex form. This is just solving. This is like what you solved when you had to find out where your catapult would, how far your catapult needed to be away in order to land in the target. We just solve it with order of operations backward. What do we do first?
Parentheses, no.
Subtract 4.
We're just doing the order of operations backwards. We subtract 4.
You gotta do brackets.
What's last?
We do take care of addition, subtraction first, then division, then exponents, then we do what's in the parentheses last. So to get rid of the square, we have to square root. So what we get is we get 6x plus 2 is equal to the square root of 24. And we get 6x plus 2 is equal to negative square root of 24. That's where you split it up. When you square root, that's when you split it into two equations. Because there's two possible ways. You simplify both. How does radical 24 simplify? 4 times 6? And which of those square root? 4. So it becomes 2 radical 6. I meant to get caught up because I want the next couple steps. Some things that might trip people up. Is everyone okay with what we have so far?
Not at all.
Jeff, did you need me to go over anything? Again.
I'll figure it out.
We have 6x plus 2 is equal to 2 radical 6. 6x plus 2 is equal to negative 2 radical 6. To get x by itself, what's the next thing to move? We would subtract the 2. 2 radical 6 is a irrational number. Subtracting a 2 is a rational number. Irrational numbers and rational numbers cannot be combined. It's like trying to combine something that has a variable with something that does not have a variable. So we would just write it as this. 6x is equal to negative 2 plus 2 radical 6. These two cannot be combined, so we just write them out side by side, and we put the negative 2, we put the rational first, because if you put it at the end, it makes it look like you're doing the square root of 6 minus 2. Does that make sense, everybody? Putting the negative 2 first keeps you from looking like you have the square root of 6 minus 2, which could be mistaken for the square root of 4. So we always put the rational number first. We're going to do the same thing over here. Subtract the 2. We get 6x is equal to negative 2 minus 2 radical 6. Want same reasoning. Minus 2 is a rational. Minus 2 radical 6 is an irrational. Those cannot be combined. The last step in both of these is to do what? What do we divide by 6? Everything. So we do one big fraction bar over 6. Let's think about this. Is this 2 rational or irrational? Rational. Is this 2? The 2. Is the 2 rational? Yes. Is the square root of 6 rational? No. Is this 6 rational? Yes. So this 2, and this 6 are all rational. They're all what kind of numbers? Well, they're all real, but they're all even. Is what I'm looking for. They're all even. If they're all even, that means they can all be divided by what? 2. So we're going to simplify this to negative 1 plus radical 6 over 3. It's putting a 1. You can put a 1 here. It's not necessary because you're multiplying by radical 6. 1 times anything is that anything.
Yeah, 1.
So the question would arise, why didn't we divide this 6 by 2? This 6 is a what kind of number? Irrational, because it's inside of a radical. So it cannot be simplified. You can only simplify the rational numbers. So if you want to put the 1 there, that's okay. And then the other answer is negative 1 minus 1 radical 6
over 3.
If all the rationals can all be divided by something in common, you have to do that. You have to simplify it. At the beginning of the year, we talked about if you have two fractions, or if you have a plus b over c, that's the same as a over c plus b over c. That's never what we're doing here. We're taking this, splitting it up into two fractions, and reducing, and then just putting it back together afterwards. Okay? You will not typically see anything that takes this much work. Okay, there's. Alright. Like I said, guys, this is the only day that we're spending on this section. So tomorrow we're moving to the next section.